Yeah, I can see.
And,
We can see.
Very good.
那我先用中文介绍一下啊。Shlomo 教授是以色列巴以南大学统计物理、圣流理论、网络科学领域的国际著名学者，同时也是以色列科学院复杂网络中心主任，曾任以色列物理学会的这个主席，研究领域涉及数学、物理、大气、海洋、经济等等。他将网络科学与统计学应用于交通、生物、金融等复杂领域，在 Nature Science 上发表论文32篇，发表了包括11篇，另外发表的包括11篇 Nature 主刊、16子刊 Nature 子刊、16篇 PNAS、68篇 Physical Review Network 论文等重要的这个科研成果，这个论著12部，同时呢是北影次数最高的以色列科学家，文章北影超过95000次 ，H 指数达到137次，获得过以色列这个最高奖，以及这个以色列国家最高奖，这个奖呢是4年1度，每届是1到2位学者，而这个 Shlomo 教授呢他是获得这个最高奖的，另外呢是囊道奖和这个等等，以及以色列诺斯特尔德奖、美国物理学会利林菲尔德奖以及以色列威斯曼奖等在内的多项荣誉。这个今天呢非常高兴的是 Shlomo 教授，我们的老朋友一起又来到我们的这个线上。由于这个线上是特殊的原因，所以我们在这里呢这个邀请到 Shlomo 教授在线上给大家做报告。那么welcome Professor Shlomo to our conference, and now please invite us.
Thank you very much
to your lecture, please.
Thank you very much, everyone. Thank you for inviting me. Thank you, Gao and everyone. And I'm very pleased to give you a talk. This good afternoon to everyone. And my talk will be today on spreading phenomena using network approach. I'm happy that Yanjing also spoke about before about spreading phenomena, spreading of messages or fake news or something. So I will speak on three topics of spreading. What is written here in the right: epidemic COVID. First, I will start, then fake news. Recent work that we did, and also cascading failure infrastructure, which also failure spread also. If you have one failure, it can lead to another failure. I will not speak about other spreading like this, for example, spreading of bankrupts in finance, but there are papers on this, spreading of traffic jams, spreading of human flow, because of short of time. Now, I want to mention these people which I collaborated on this work, Alexis Jian and Gao Dong, and to thank them, and Chiasong Chen and Yanqing Hu gave the talk, and Jim Fang Fan, Louis Ekman, and Benaya Gross and Fan Wang. Some of the papers that I give here are presented this work, which was many of them was published just this year, like Benaya Gross on this one, and also a paper that's just going to be published by Yang Liu, Gao Dong, and Fan Wang, published in National Science Review, which is very relevant to COVID. Fake news is a paper that's published this year, and about cascading failure, published in several last years. So let me start with the first topic will be the epidemic or the pandemic COVID-19. So in this work, we analyzed the temporal and spatial propagation of COVID pandemic in the beginning of the epidemic in China, in the first few months. And it started from Wuhan, from Hubei. And we wanted to see if we can see some spatio-temporal propagation. And we find that if you look here, R is defined the distance from Wuhan, from Hubei, of the cities. I is the total number of infected. And M is the population of the city. And we find several laws which are represent the propagation, the spatial-temporal propagation. For example, if we look on the number of infected as a function of distance from Hubei, the assumption was that people start from Hubei, moving to other places, and we see that these are different cities. Each one is different city, how many infected, different cities in different distances, from 600 kilometers to 3,000 kilometers. And you see that there is a decay, which is like a power law, which is an exponent of about -2. When we look on the infected as a function of the size of the city, M is the size of the city, we see also kind of power law. So what we can see that if we make the function, the infection as a function of distance versus mass, because we see that the mass increases, and as a function of minus gamma, we take here power of minus gamma, we see a nice power law that represents this when gamma is about minus 0.84 plus minus 1, it's close to 1, the decay of the infected. But what is, I think, the most interesting part is the next figure, where we look on the number of infection, and we had also data how many people move from one city to other city in this time after the starting of the epidemics in Hubei, in Wuhan. And we can see that the more people move from Hubei from Wuhan to other cities, these are the number of people that moved it this day, the more people were infected. I think this is a very strong argument to show that almost linearly that the epidemics came to other cities because of movement of people, most of it because it's almost linear. More people move from one to other city, more people were infected. And also we can see here the population migration was less than, population migration in general is more than the infection, because of the exponent here is 1.37 and here it's 1.84, because there was some restriction, but not much. This figure was before the strong restriction of moving of people. But of course, when you make the restriction, it becomes much less infected. So the main point is we want to show here is that actually that everything that was in China was very much dependent on the restriction of movement from one city to another city. We can see here also other figures like population migration as a function of M and population migration R over M. But I think the main figure you can see here, which is the number of infected, was proportional to the number of population migration. And this is in this paper, which appeared a few months, 2 months ago. Now, so what is happening in China compared to other places? So we compared here how the number of infected increases in China in the first months in January, February, and we can see it stabilized. While when we look on the same time in Italy or other places, we see all the time it increases. And we can look on the probability of infection, which we plot here in the right, and we can see that a very nice difference between the decay. This is the decay after the restriction, how the probability of infection decay as a function of time. And you can see in China, it was decaying much faster. First of all, we believe it is exponential decay, because this is a log scale. You see a power, this is a log scale, and this is a linear scale, and you see a nice linearity. So these are the infection decay in China, much faster than the infection decay in Italy, for example, after restrictions. So it means that the restrictions in China were more powerful. And indeed, if you measure the number of days, because of the slope, you can measure the days of decay. It took about 10 days in China to decay, while 10, 15 days, you see, while in Italy, the decay was about 40 days. So you had a much faster decay here. This is the decay here. You can see 15 days, 16 days. The parameter that tells you what is the typical number of days that it was, and you can see all of many Chinese cities, the decay was much faster than in Italy, where it was much slower. So all these results suggest that actually the restriction was very efficient in China, while not so much efficient in other places. So this is what I'm telling you about the epidemics, the pandemic, and now I want to go what to do about efficient immunization. How can we immunize efficiently? So already in 2003, this paper, which is very well cited by Cohen, my previous student, now is the professor of mathematics, we suggested a simple way to immunize people, how to choose the people to immunize, which, of course, if you choose the people that are most connected, this is very good. But how do you know them? So instead of making to find them, you just take the network, the people, and you ask everyone, give me a name of your friend. And instead of immunizing him, you immunize his friend. Not the most connected friend, just a number of friends. If you immunize randomly, then you will need about 100% of immunization because the social networks are usually scale-free. So you will need QC, the fraction of immunization unit will be almost 100%. This depends on lambda. Lambda is the parameter, but lambda for our case is about between 2 and 3 usually. So you will need 100%. Now, if you make targeted, means you only immunize, you know the hubs, you know those that are well connected, and you immunize them, then you need about 10%. But we don't know the hubs. We know only some people, but we don't know the hubs. So how to find them? So a good way to find them is by using acquaintance immunization. It means to choose randomly people and to ask them, give me a name of your friend. And usually you can see here, this one, it may give this one with high probability. All these will give this one as high probability. So if you have a higher probability to locate the hub by this way, which we call it, and then what happens, instead of having 100% you need to immunize only 20, 30%. This is acquaintance immunization of the one. It means you reduce the number of units that you need to immunize by a factor of 3. You see, between 100% to about 20, 30%. So this is the method where you can immunize efficiently population and also computers or anything that you want. Not by knowing, you don't know the network, but you just ask people, tell me a name of your friend. And then you immunize the friend instead of the people, you reduce the number by a factor of 3, more than 3. And so it becomes a poor immunization when you make it randomly. It becomes efficient immunization because usually the friends are hubs. And then how you immunize them. But now, recently, we had a paper with a group from Nanjing, the paper with Liu and Yang Liu, Gao and Wang, which is published it will appear in a few days. We have another method. We say, okay, we don't know, people don't want to give the name of the friends. So why not to do another method, which is very easy to do, is to choose a number of people and to ask them some questions. For example, you go to a supermarket, to a shop, and then you find out who is the most connected one, and you immunize them. And the surprising result, it means instead of finding the hubs, you just find some people, and you ask them, give me, and you immunize the most connected one from this. For example, here, I choose this one, I choose the green one, this one, and this one. And instead of immunizing these 3, these 2, I immunize the one which has 4 friends. And by this way, by this method, I don't need to know the network, but I need to know only some people. And you can see here that instead of having PC means the number of non-immune. The number that you don't immune, but the number that you need to immune is 1 minus PC. You need to immune here about 80%, or here you need to immune about 95%. But if you take 10 people and you ask the most connected one and you immune them, then you reduce it from 20% to 450 to even from 80% to 25%. And here also, this is scale free, it's even more sharper. You see, instead of immunizing everyone almost, you need to immunize only about 20% of the people. So this is efficient immunization, not by looking on the most connected one, but you can find them easily by taking a small group of people and find from this small group of people who is the most connected one, and then immunize them. And indeed, we did it also on social networks, on several social real network. We tested it, and you can see that these are 6 types of social networks, and you can see the method. If you take only one, it means you randomly you choose one and you randomize it. Then you have the PC is about 0.1. It means 90% you have to immunize. But if you take already 2, and from the 2 you choose the most connected one, it reduces by a factor of big factor. And also if you take 10, you see instead of being 10%, it becomes you remove, instead of being 90% to immunize, you need only to immunize 20%. And this is very general for real networking. We don't assume any structure of the network. Now, I will go to a little bit to spreading, another spreading phenomena, where we can also find a distinction between fake and real news spreaders. And if you look on the picture, we had many data from fake news from China and from Japan, and of real news from Japan and China. And we find typically there is a difference between the network of spreading of real news. There is usually origin is very dominated, while in fake news, people like to spread it more than in real news. And that's why you have a picture like this that many make their own spread. They become again a spreader and spreader. And this was published in EPJ Data Science just this year. And we wanted to have a measure and to test how much we can distinguish automatically of fake and real without knowing the text. Of course, if you know the text, you can do it better, but with the structure, you can do it even very good without knowing and we can see here also, again, the Weibo and Twitter. You can see that in the fake news, you see you have many layers here. It means this is how much, this is the time in hours. And you can see already after 1 hour or 2 hours, you have already several layers. Layers means that it goes from this one, it goes to this one, this is one layer, and then it goes to this one, another layer. So we can see many layers, while in real news, mostly you see 1 or 2 or 3 layers, not more. So how to distinguish? We just have a very simple method. We check the heterogeneity of the network. The heterogeneity of the network is just, we define it like we have 2 parameters here, k and k squared, and k is the average of the degree, and k squared is the average of the square of the degree, and the heterogeneity is defined by this function. Of course, if you have big heterogeneity, then you see that the number is large. But if you have a star, only a star, the number is large. It can be 1. But if you have it depends also on n, on the number of nodes. But if you have small heterogeneity, yes, you see smaller numbers. And indeed, when we put hundreds of or thousands of fake news and real news, we could see that when we make them heterogeneity, and here we put the size of the network, we can see that mostly the false are in low heterogeneity, and the high, and those of true are in high. And then we make a way to distinguish between them, and we find that we can predict almost 80% of the fake news just by looking on them in few hours. After a few hours, you can say, is this a fake news or a real news, depending on the heterogeneity of the system. So, and of course, if you include also machine learning, you can improve this much better. Now, another spreading that I want to speak. This is the spreading of cascading failures. And if you, every one of you probably remember that almost 10 years ago, there was a cascading disaster in Japan because of the earthquake. There was a tsunami, and the nuclear electricity did not work, and then it was cascading that also transportation didn't work, electricity didn't work, and all the services stopped function. And I remember this day when I got up in the morning, I was in Boston, I saw in the hotel this paper. I said, oh, this is exactly, and I went to give a talk on this, so I copied this paper on this day, on Monday, March 14, 2011, because it represents the big damage that can be done from cascading disaster everywhere. So, and the question was that we didn't know how to study it. But what we found that already engineers, even earlier, before 2011, 10 years ago, 20 years ago now, almost 20 years ago, already make the puzzle of how interdependent our infrastructures. Everyone knows that you cannot have only power grid. For the power grid, you need natural gas, you need transportation, you need oil, and vice versa. For the oil, you need electric power, and for the telecom, you need electric power, and vice versa. So all of these are dependent, and this was known, but there was no tool to study this and to study the cascading failure, because if you have failure in one system, it leads to failures in other system and other system, and so on. You get a big failure in the system of systems. And indeed, there was an example in 2003 where there was a blackout in Italy in 28th of September 2003. And this blackout was caused by, it was found by Rosato, engineer in Florence. In 2008, he studied it for 5 years, and he found the reason for the cascading. It was failures of power grid here, led to failure in the communication system, the SCADA communication that controlled the power grid. And this communication led to further failures of other, because if you don't have communication, the power grid system cannot function. And this led to cascading failure, and that's why railway did not work, and the health service didn't work. But there was no theory for it. So what I want to show you is a theory that can explain the cascading failure and can also teach us how to avoid cascading failure. So I will give you this topic, and the main 3 points that I want to emphasize here and are written here. This is like a summary. First of all, the cascading failure. If you can see here, these are 4 networks. They could be infrastructure, they could be also other networks. Even it can be even in our body network, many systems, they interact with each other in the physiological systems, and one system needs the other one for functioning. You cannot function, the heart cannot function if the brain doesn't function, and the breathing system doesn't function. So this is a general picture of interdependent network and what we see here is that we have one network, and each network is for a different function, but some nodes in one network depends on functioning of other nodes in another function. And this can lead to cascading failure, and not only cascading failure. I mean, failures here can lead to failures here, and can lead to failures here, and failures here, and back to here can be a feedback. But not only cascading failure, it leads to abrupt collapse, and this we can show in analytically, as I will show soon. And then I will show you that we can generalize percolation theory, not that was done until 10 years ago, for 60 years, only for single networks. We can do it for a network of networks like this. We can have a theory for percolation in network. It means if you have random failure in one network, how does it lead to other failures in other networks, and how does they come back also? And the third point I want to summarize is a very important point. Is we know that usually infrastructures, many systems, even the brain, is in space. And in space, the system become much more vulnerable. It means that small attacks can lead to big failures, and even localized attacks, small attack in one system can spread to other system and come back to this system and can make the whole system to break down. So let me start first with cascading failure or abrupt collapse. I will show you what was the theory in a single network. So in a single network, you can see here, either the system is very simple, like exponential network, or scale-free network that have a different distribution. In both cases, if there are failures in the system, some nodes fail, still the giant component, the component which controls the system, is still functioning and goes continuously if more and more failures. This is P1 means all of them are functioning, all nodes. But if I have P.9, it means that 10% of the nodes already fail randomly, for example. And then for ER network or Erdős-Rényi network, this exponential type of network, we see that the system becomes smaller and smaller until a certain critical point where the system collapses. This is for this system. For this system, PC becomes almost zero or zero even, because it's very well connected because of the hubs. So you need to find the hubs in order to kill them. But if you randomly choose, the system is still functioning until it comes here. But the big important point is that the size of the system is continuously going down with the failures. And this can be seen because why it goes down not linearly, because if I have some failures, for example, it's not only that this fail, but also it leads to other failures because some clusters also fail. That's why it's not linear, it's going down faster than just the number that I remove. Now what happens if I take two networks and they are dependent? And if they are dependent, like here, these are the same two networks, I take them here, dependent. I don't see, and now I have failures here, I don't see anymore the continuous transition that was here. By the way, this continuous transition for a single network was studied already in 1950 or 1959. It means almost 61 years ago by Erdős-Rényi, and find the formula for the giant component. It means this as a formula. It means that the mathematical formula tells you how big is the system when you remove randomly nodes from this. The same, there is a formula for scale-free here, mathematical formula. But instead of this, we see when you start to remove, but you have also dependency on other nodes. It's not important if you have bidirectional dependency, like this node. This node depends on this node, and this node depends on this node. But also if you have one directional, for example, only this node depends on this node, or this node depends on one. What happens is when you have enough failures in one system, just one node more to fail leads to abrupt collapse, cascading appear here, and the system collapses to zero. And this makes the message that our world is very unsafe, extremely unsafe, because we have dependency in our world, and the world becomes more and more because of the modern technology. Dependency becomes more and more plausible, occurs. For example, now if I need the telephone, I need the internet also, otherwise I cannot make a phone. If the internet doesn't work, and 20 years ago, it was not like this. So we need to better understand how abrupt collapse can occur. And we need to understand better this. So what we see here, that because of the dependency, you cannot go continuously down to zero, the chain component. It goes in a certain point, it jumps to zero by abrupt transition due to cascading failures. So this was the point one, that you have abrupt collapse. But this is only, I show you by simulation. Now, can we do analytically this? So what I will show you now is how we can generalize percolation theory to network of networks. And I will give it only very shortly. So we study here, for example, network of networks. It means a tree of networks, like all the networks don't have loops. Each node is a network. You see this node is a network, this node is a network, every node is a network, but the nodes here depends on the node here and vice versa. And the same everywhere. And if we took 5, But what we find is that if you solve it mathematically during generating function and doing and making the full analysis, you can find finally that you get a formula for n networks, which is very similar to the old nice formula that already got in the 1950s, Erdos and Reini, they got this formula. But here we take, instead of one, we take n equal 5, or n in general, we get another formula. And the difference between these two formulas is only the n that appears here. Of course, if you study one system, one network, we don't need the n because one appears here. But this was not known when they solved this formula, but it's now known because when you take here 2 instead of 1, and 1 you get a continuous transition. But when n is 2, and you solve this formula, you see that there is a jump. And the jump comes because of the cascading failures between the network. And when n is 5, it becomes more vulnerable, and so on. So we get actually a generalization of percolation. We can do it for many cases, but I gave you only the simplest example for which you can have network of network, but you can have analytical formula for this, and this was published in these papers. Now, what happens during the cascading failure? This is also very interesting. And what we see that during the cascading failure, it not just jumps from here to here because of the cascading that appear failure 0 lead to failure 0, failure 0, failure 0, and back to here. But it goes in a very certain way that goes, in the beginning, it goes fast. It means if I look here, in the beginning, it goes fast. Fast means that in few iterations between the system, it goes down very fast, but then it slows down very much. And indeed, if the system is infinite, this plateau goes to almost infinite and decays very later. So this is a simulation and theory for a finite system, and you can see that you have a plateau. It means that when you reach PC here, if you measure the number of cascading here, and the number of cascading, you get a small number. But if you go here, you get a peak of the number of iterations, and the number of iterations becomes very high, which means this is represent the plateau. And also, this is very important. If you don't know what is PC, like here we know it analytically, but if you don't know, you have a system, interdependent system, you don't know, you just measure the cascading failure, and you can find the number of cascading diverges at PC. This is analogous to single system where the number of the divergence goes at PC, not the number, it goes the second largest component diverges also here. So this is also a critical phenomena that has critical exponent and was studied carefully. Now I want to come to a work that Yanqing, I'm sorry the mistake here, Yanqing who gave the talk before me, which is a very nice talk, how to avoid this abrupt transition. And to avoid this abrupt transition, we suggested to take some decentralization of the network. The reason that these clusters fail, is because they did not have, they were not connected to the giant component. If they are not connected, they cannot get electricity or they cannot get communication. But if you give them extra communication or extra electricity, this is alpha. So this is, let's say, electricity we give him. And this can we give the extra connection, and this extra electricity can support not only him, but also his neighbors. Then the giant component becomes very large. You see, it includes also these three. And here, if this includes it as also, then it includes also this. So it means that you introduce decentralization, and this is a paper that was published 3 years ago, by Yanqing Hu and students. And we find that it can, with a small fraction of nodes which are reinforced, which are decentralized system, that you give them extra functioning, you can reduce the very much the abrupt collapse. And it's very important because if we knew this before Italy, we could say, okay, this one, give him also more connection to another alternative connection, which is not the connection here that was killed by this. So if you choose here or here some extra connections, you can solve. Actually, they can do it now. And we can see also analytically what is the raw critical, how much you need, maximum fraction of reinforced nodes in order to stop the epidemic, the cascading failure. And you can see that for Erdos Reini, it depends also on Q. Q is the fraction of dependency that I have between the system. And you can see that if the fraction is higher, but still 75%, you need only a few percent of reinforced nodes. And here you need also very few percent reinforced nodes to stop the cascading failure. And indeed, we made a test for the power grid in USA, and we see that if we don't give reinforced nodes, you see the system collapse here after 12%, or if it's scale-free, the communication system after 10%. But if you give 2% or 1% here or 5% here, the system will collapse very smoothly. It means it will not collapse abruptly as we are afraid of. So this is the second point. And now I come to the last point to show you that if you have dependency, as we have here in every infrastructure, it means if you have dependency and you have both, also you have spatial networks, the networks are in space, it means that the links are are short range, then localized attack can lead to a collapse of the system. So we have actually two models for this. I will give it very shortly because the time goes fast. One model is connectivity links are large here, but the dependency in the same position. Here we have a connectivity are short, and the dependency can be farther away. And these two models are justified by, in particular, this model is justified because the connectivity links can have also a characteristic scale, as we see here in the power grid. We measured it. This is the power grid. You see it as an exponential decay, and here it has exponential decay in Japan, the local rail, and there is a characteristic length of the connectivity links. It's not that they have the same lengths everywhere. So if we choose this as a model, we can see that both systems behave in a very similar way. What is the similar way? Now we have two parameters. One parameter is how far is the connectivity. This represented by zeta, and R tell you how far is the dependency, how far I can go dependency. So we can see here if the dependency is small or the connectivity is small, we get a continuous transition. But when the dependency goes above about 8, it starts to be abrupt transition. PC becomes different. You see a peak here, and this becomes abrupt transition. It means if the dependency is above 8 units in this system, in a lattice, or 10, 12 units also in this system, you get abrupt transition. So you have actually phases which are continuous, phase which are abrupt, and this phase we don't know, it's not clear, and I will show you what is this phase. So this phase is the system is stable. This phase is the system is stable. But what is this phase? And this phase is the following solution in both cases. You can see it in this paper, or in I gave here also in a paper which published in PRR in 2000. So you can see here, you have actually the phase diagram is behaving like this. You have actually three regimes. One regime below here, or below here, where the system is unstable. It means the system collapses anyway. And the green, which is small here, is the system is stable. This is this regime here or here. But you have another regime which is quite big, is a metastable state. And this metastable, we found that the localized attack above a certain radius can spread and can collapse the whole system of systems. It means, and this size of the critical size localized attack depends where you are in the K and the R. This R can be R or zeta, it's the same. And you have a metastable state, and you can see it here, we have simulated here. if the size is smaller than a certain radius, it does not spread. If the size is bigger than certain radius, it spread. And we show here on the European power grid that if you spread just randomly the same amount that you put locally, there's a big difference. The randomly does not spread, but the locally spread and destroy the system. And this is a big surprise because now we have a new percolation that even if for PC1, it means you don't need to remove a fraction of the system, like in regular percolation. You just remove a zero fraction of the system. It means PC is 1, and you still can get, and you can see it here, the number of the that you remove does not depend, if you make a localized type, does not depend on the system size. So let me summarize. I showed you several spreading phenomena using network approach. First, I showed you first this one, that spatial temporal spreading and efficient immunization comparing China and Italy. And we saw here that the decay in China was very fast. You're lucky. You don't have, but Italy, they still have here now. In America we have, and we have in Israel. But the first restrictions in China was very efficient, and that it decayed exponentially in about 10 days. Fake news and real news, I showed you a simple parameter. The heterogeneity can tell you which, in the first few hours already, what is fake and what is real. And the last thing is started in 2010, is network of networks and how to analyze network of networks. And we showed you have also a plateau here that the cascading failure do not fall immediately. And then you have also many other spreading, which I don't have time to speak. And I want to thank you very much. And if I have time for questions, I would be happy to answer. Thank you. Hello?
Sorry.
Can you hear me?
Sorry, Shlomo. Thank you. Yeah, I can hear you. Thank you very much.
Sorry. Just, not open the single. Yeah. Thank you very much, Professor Storm. And this is a very nice. Very nice report. And now maybe someone any question? Go go.
看看其他人还有什么问题吗
Hello, Shlomo.
Yes.
This is Jingfang.
Can I hear the question? I cannot hear the question, maybe.
Oh,
hello,
here is
Shlomo. I have a
Jingfang.
question. Hello,
Who has
Shlomo.
the question?
I have a
Hi,
question,
Jingfang.
Shlomo. Hello, how are you?
Yes.
Yeah.
Good to see
just
you.
one question. Just one question about the spreading phenomenon. Can your model forecasting the second waves of the coronavirus in Europe or in US? Can you forecasting or can you
No.
do some measure then to stop the spreading?
No, we can. What we can do, we cannot forecast. We don't have a method to forecast the second wave, but we realized that in China it was very effective, and maybe this is the reason why you could not have a second wave. But but what we can do is we can suggest a very efficient way to immunize the spreaders in such a way without even knowing that they are spreaders. You see, if you make a coincidence immunization, or if you choose 10 people randomly, or in a supermarket, and you find out who is the most connected one by filling some questionnaire, how many people he meets a day, does he go to work, how many people he has in work, or is he a teacher, or something like this, and give them, you can see that you can reduce the number of immunization units by a factor of 3 or more even.
Okay, yeah. Thank you, Shlomo. Yeah, I got it.
Thank you very much.
Thank you.
And
Yes,
maybe
thank you very much for everything.
Maybe someone any questions to communications with Professor Storms, and thank you very much again.
Thank you very much, Shlomo.
Thank you very much, everyone.
The next